Hi there. In this lesson, we get to get into two proportions, so I'm really excited for that, and we're going to start with confidence intervals. Okay, so let's read this example. So we've got confidence intervals for two proportions, and we have juvenile diabetes, which is type 1, is usually diagnosed in children and has a genetic component. A study enrolled 76 children who are at high risk for the disease. The kids were randomly assigned to either a 2-week intravenous course of the drug teplizumab or a control group. No idea if I'm saying that drug correctly. The study ended when 42 kids developed the disease, and the results are shown in the table. Okay, so here we have a whole table, and one of the things that's going to be important when we have a whole table is picking out which numbers do we need to use, because there's more than just two proportions in here. So let's read what we're going to do first, and I'll talk a little bit about the table also. So this says, find the proportion in the control group that developed diabetes. Okay, the proportion in the control group. Okay, so let's look at our table here. We've got one way will be the outcome or response, and the other way of the table will be the groups, okay, or the input or explanatory. It's not always groups, but it often is. So it does help to determine which is which, okay? So it looks like we've got here on the rows, control group and teplizumab group, okay? The drug group and the control group. So these are the groups. Okay, I'm going to write that there. And so these often are what we're comparing, are the groups, right? And then we also want to, what we're measuring is the response for each group, or the outcome. Now, the wording of the question will tell you which one are we counting. Are we counting those who did not develop diabetes or those who did? Okay, in this case, it says that developed diabetes. Okay, so see how it tells you which outcome to look at? So I'm going to put an arrow down here for that first column for the response. Okay, so in this case, we are measuring the proportion that developed diabetes, and then we have two different groups, right? So part A here is saying for the control group, so that's going to be 26, and we're going to go over to the across that whole first row to the total of that group, which is 38, right? So there were 38 kids in that group, and that a total, so 26 out of 38. So let me write that. And notice with this p hat, there's a C on it. So since we're going to have two different proportions, we will use either a number or a letter to distinguish the two. So that's a subscript. So C for control is what I picked in this case. P hat sub C equals 26 out of 38. Okay, and let's look at the second part. Part B says find the proportion in the treatment group that developed diabetes, and that's P hat T for the drug that starts with a T. So P hat T, and it makes sense. We should be comparing the groups, right? So the denominator should go with the groups or whatever the explanatory situation is. So diabetes is 16 out of the same total 38. So in this case, they had the exact same number of kids in each group. They don't always, so they won't always be the same, but they're often close. 16 out of 38. Okay. So you'll notice there's a bunch of numbers we're not using. We're not using the total of diabetes or total of no diabetes, or really the grand total at this point. Okay, so we want to know, are these different? Are they the same, right? Was this drug effective? That's what we want to know, or how effective was it? So to compare the two groups, we're usually using a difference, right? What's the difference between the two groups? Okay, so difference means subtraction, and often a question will tell you which way to subtract. It really can be done either way. You'll just get a difference of a positive or a negative sign. But I recommend if a question tells you to do a certain order, then just stick with that order. The the coding, if it's My Open Math or something, the coding might be dependent on that order. Okay, so the difference, we're going to do control minus teplizumab. So you can see it's shown both ways, both in words, control minus teplizumab, and also with the symbols p hat c minus p hat t. Okay, so p hat c minus p hat t. And I am not going to divide these individually because then I'm going to get round off error. I don't want to round and then subtract. So I'm going to write the whole thing, 26 over 38 minus 16 over 38. And they do have a common denominator, so you could do 26 minus 16 over 38. I'm just going to, because we won't always have a common denominator, I'm going to treat it as if they're not. 26 over 38, which I'm just using the division button, 26 divided by 38 minus 16 divided by 38. And because division comes before subtraction, it's going to subtract those two fractions for me. You can also use a fraction feature on your calculator, but then you might get a fractional answer in which you might have to turn that into a decimal answer. Okay, so I'm getting 0.263 and round that to 2, 0.2632. Okay, another thing to notice is the sign of the difference, right? So if the first thing is bigger, if the control group is larger, then, and you subtract something smaller, you're going to have a positive left over, right? So, which is the case in this one. And control, so developing diabetes is not what we want, but we do, you know, ideally the drug is useful, and so the control would be larger. So often it's set up to get a positive result, but not always. It's good to have practice with both. So I just want to make a note, since this difference is positive, that means the first proportion is bigger, right? So we're gonna, the thing with two proportions is we need to figure out which one is larger and by how much, okay? So if the difference is positive, then the first proportion is larger. Okay, if we get a negative difference, then our second one, if you subtract something bigger from something smaller, like if you spend more money than you have, you go in the negative, right? Okay, so that does seem to be a difference, right? We want to know, is this difference significant, or how can we estimate the difference for the population, right, of kids that might take this drug? So we're going to get a confidence interval for that. So we're going to find a bootstrap, so that's our simulation with confidence intervals, a bootstrap 95% confidence interval for the difference, and write the interpretation. Okay, so let's switch over to StatKey for that. That's going to be the tool we use for proportions. And bootstrap confidence intervals are in the center column, and we're going to CI for difference in proportions. Okay, we've used the first two. We're skipping over difference in means for now. We'll come back to that. And confidence interval for difference in proportions. Okay, and just like you're used to with StatKey, there are some built-in data sets. You might be directed to some of those in homework or assignment or quiz. And but for this one, we're going to use edit data. And so if it doesn't direct you to a specific data set, we just enter our own. And you'll see we have space to enter two proportions instead of just one. So I'm going to keep that same order, 26 out of 38. 26 out of 38, and then 16 out of 38. Okay, so let's hit enter and check this out over on the right hand side where it says original sample. We can double check our inputs here. So group 1, and this uses 1 and 2. Group 1 is 26 out of 38. It does give us the decimal version of each individual proportion. Group 2 is 16 out of 38, and then group 1 minus group 2. It does the difference in the counts. So just like because we had a common denominator, we could say that's 10. Out of 38, it doesn't do a sample size for that, especially if they're different denominators. And then it gives us the proportion. So that's what we calculated, 0.263. And because this only uses 3 decimal places, that is what we got. We got 2632. Okay, so remember what bootstrapping is doing. It is taking this one sample, reshuffling. So right, imagine we have 2 different sets of cards. We've got a group 1 and a group 2, right? And so it is going to shuffle all those together and then draw a new sample. So let's do one at a time here. Okay, so it's taking, so there's 38 and 38, so it's keeping the 38 and 38. And then this time it got, 28 instead of 26 and 12 out of 16. Okay, so it's like we have 2 different sets of colored cards and it's reshuffling. We have one for group, one for the control, one for the drug, or group 1, group 2, and then how many kids developed diabetes and did not develop diabetes. Okay, so there I got a difference of 0.421, so that's even larger. Let's do a couple of these, and you'll see the numbers will change each time because it's drawing. It's, all right, so what I forgot to say is it's putting them back in, drawing them back out, right? Bootstrapping is, because we only have that one sample, we can't draw all of them because we'd get the exact same sample. It's drawing one, recording it, putting back in, shuffling it up, drawing one, recording it, putting it back in. So we're sampling with replacement. Okay, another sample, and what's just amazing is the standard error comes out very, very close to if we knew the population. Okay, getting the idea. So each time we're getting 2 different groups, counts of those who would develop diabetes, and then taking the difference. Okay, so here the difference is smaller. Oh, actually it's right on. Let's see if I can get one smaller. There's a smaller one, 0.158. Okay, let's go ahead and do 2000. Okay, and then just like we did with our single proportion before, when we want a confidence interval, we click on two tail, and the confidence level goes in the center upper box, right? We're capturing the middle 95% of all the simulations, and what are the boundaries of those two. Okay, so this is saying from 0.053 to 0.474 captures the true difference between those two proportions. Okay, so I'm going to write that down, and then I'll switch back to the notes. 0.053 to 0.474. Okay, we'll go back to the notes here. So I wrote that down, and then we're going to, that's our confidence interval. Remember, it's for the difference in the two groups. We're going to write the interpretation. So this will be a little bit new, because how do you write the interpretation for a true difference between the two? Okay, so let me show you that. So we'll start the same. We can be 95% confident. That the true proportion of kids who will develop remember, we're inferring to the population, so we're not just talking about the ones who did develop, but those of kids in a similar situation who, similar risk categories, will develop type 1 diabetes is, and often it does help to change these into percentages. So I'm going to do that, is 5.3% just makes it easier to interpret, to 47.4% higher. So we've got to also say the direction, right? We're measuring the risk of developing diabetes. So the true proportion of kids who will develop type 1 diabetes is 5.3% to 47.4% higher without the drug, meaning the control, than with teplizumab. Okay, so we could have also switched it the other way, but as long as you know, there's a few different ways that work. Okay, as long as you stay consistent. We could have said lower with the drug as well, but it just kind of made sense with the way this one was set up, with the control being first, and it is was higher in the control group. Okay. So we'll get some practice, more practice with that. Main thing is we need to say which is higher, because remember, we can't assume that anyone else is going to understand how to figure that out. That's our job. Okay, so at the bottom here, I have a screenshot of a simulation that I did, and you'll see it actually is very consistent. It came out the exact same way. So remember, here's our confidence level, and then we have our bounds at the bottom, lower bound, upper bound, and the default is 95%, so we didn't have to change the confidence level at this time. And then also, just for future reference as you're using your notes, let's circle the sample proportion that is the difference of the two. So the group 1 minus group 2, which is 0.263, that, let me squeeze it in here, it was the p hat C minus p hat T. Okay. So you always want to double check that. And remember, since we're doing bootstrapping, that should be the center of the graph. So that's another check that you're in the right app versus a hypothesis test, which has the null value in the middle. So you can always double check that p hat is correct, and or difference of p hats is correct and should be in the center of your confidence interval. Okay, so I'm going to go to the next page, and let's look at a different confidence level. So let me scoot this up a little bit. Okay, can we be confident at the 99% level that the drug teplizumab is more effective than the control? Find the bootstrap confidence interval and explain. Okay. So at the 99% confidence level, so let's go over back to our simulation. And this time we do need to change that middle box to 0.99. Okay, so let's see what happens here. Okay, so we've got 99. This time it's going from negative 0.026 to positive 0.553. Remember, it makes sense. Higher confidence means we need a wider interval because we're now capturing the middle 99% of those same simulations versus the middle 95%. Okay, so what do you notice about this? It's going from negative to positive. In other words, 0 is a plausible value. 0 is in our interval. Okay. So while we could be 95% confident that there's a difference, at the 99% level, we cannot be confident that there's a difference between the control group and the drug group. Does that make sense? So let's write that out. So I'm going to first write my values before I go away from here. Negative 0.026 or 2.6%. Oh, whoops. Didn't mean to close my parentheses yet, comma 0.553. Okay, I'll go back to the notes. Okay, there is I've got one little dot there. There we go. Okay, so negative 0.026 to 0.553. So the way we would write this one is, I don't want to use quite the same way I wrote the other one. When 0 is in there, we're going to say there's not a significant difference. Okay, so since 0 is a plausible value for the difference, there is not a significant difference at the 99% confidence level. Need to get that in there somewhere. I'll put a commas around that. There's not a significant difference at the 99% confidence level. Then I got to put my context in there, right? That are not a significant difference in the true proportions of kids who will develop diabetes in the drug and control groups. Okay, we can't say which is higher because it could be because one's negative and one's positive. That means the control group could be higher, or the drug group could be higher. I may not have pointed in the right order in those, but we'll get more practice with that. Okay, so this is very different than we've been interpreting just one proportion. Okay, so isn't that interesting? Let's see, I do want to just make a note. I'll also kind of make a note here about which one's positive, which one's negative, and then we'll fill in this table on this page as well. Okay, so if the difference is negative, then the second proportion is larger, which in this case was the treatment group. The drug also started with a T. That's kind of nice. The treatment group. Okay, and then if the difference is positive, just like we were talking about before, then the first proportion is larger. And that was the control group. Okay. Great, so I hope it helps to see that in terms of this example. So let's write out, so you're probably kind of gathering, there's three different possible things that can happen. Three different directions. So we could have positive to positive, which was like the first one we got. In that case, P1 is greater than P2. Okay, and I'm just going to use the 1 and 2 for now, but it could be whatever letters we're using. Okay, and I'm using the population, not using the hats, right? Because we're trying to estimate. We would be estimating that P1 is larger than P2. Okay, and so our interpretation would go with whatever percent confidence, the true proportion of blank, right? So that's whatever we're measuring, that's our variable, is blank to blank percent higher for group 1 than group 2. So that's a lot like how we wrote out the first interpretation. Now, it's also possible to get negative to negative. I'm going to adjust my paper here for a second. Negative to negative. We haven't seen that case yet, but it would be the opposite of the first one. That would mean we would be estimating P1 to be less than P2. Okay, and if we just flipped the order of our proportions, we would get this case, okay, but the end result would be the same. The meaning would be the same. It would just, the wording would all be flipped. Okay, so there we would say with whatever percent, C percent confidence, the true proportion of whatever we're measuring, a variable, is blank to blank percent lower for group 1 than group 2. Okay, and let me underline or circle the higher from the first one. Okay, now something interesting for this one. We don't want to interpret negative percents. We don't want to say this is negative percent to negative percent higher. So what we do is we reverse the values and we turn them positive. Okay, so we can swap them and say blank to blank percent lower. Okay, so that's a switch that we do so that someone's not trying to interpret, well, what does negative percent higher mean? We need to spell that out for them, okay? Third case, negative, oops, sorry, just move that, negative to positive, and that is the other one we saw just in part E here. And in that case, we're estimating that P1 is about the same as P2, or we can't tell a significant difference between the two, so I'll write approximately equal. With C percent confidence, there is not a significant difference in the true proportion of whatever we're measuring, the variable, for group 1 and 2, or groups 1 and 2. Okay, great. So try that out, especially the reversing and making positive. I'll actually circle those. And great. I'll see you in the next video.